Hi everyone, my name is Amir, and today I'm excited to present our work titled Algorithmic Recourse from Counterfactual Explanations to Interventions. This is joint work with Bernard Schölkopf and Isabel Valera at the Max Planck Institute for Intelligent Systems. This is Edward. He's 28, he has a salary of $75,000, has $25,000 saved in the bank, and is a software engineer, and is single. He's thinking of buying a house. After months of scrupulous savings and many open house viewings, he's finally found his dream home and is ready to place an offer. But first, he must visit a bank. The bank may consult a system such as this one to decide whether or not Edward gets the loan. Or perhaps one like this. Or one like this. With more involved models, the system typically gains the ability to accurately model the nuances in the historical training data. However, it has sacrificed its interpretability. Naturally, some questions arise. The bank may ask itself, what are the most influential features towards the decision? Regulators or a governing body may ask, is the system acting fairly by relying on sensitive attributes such as age and marital status? Finally, bank customers like Edward who have been denied a loan may ask, I didn't get the loan. Why not? And what should I do to get it the next time I apply? Answering these questions is the concern of the field of interpretable machine learning, or XAI. Among the definitions of XAI, we adopt the one by Doshi, Velez, and Kim, which is the ability to explain or to present in understandable terms to a human. XAI has two broad goals. Firstly, to understand why a particular decision is output, and second, to recommend actions resulting in a desired output. One up-and-coming method that aims to achieve these goals is counterfactual explanations, which are statements of the form, if your salary had been $100,000 instead of $75,000, you would have been offered a loan. In this example, the explanation provided by the bank would inform Edward of the situation he must achieve in order to be offered the loan. Let's take a closer look at counterfactual explanations and see whether or not they satisfy the goals of XAI. Given Edward, a factual instance xf with prediction y at time t0, we seek an explanation for why his loan was rejected. Looking back in time, a counterfactual explanation would tell us that had the feature vector xf taken values of x CFE, the classifier h theta, not shown here, would have given you the loan. This is called retrodiction. Now, using the same reasoning and looking forward in time, if the world is stationary and the classifier doesn't change, at time t0 plus t, the feature vector xCFE would also result in a favorable outcome. This is called prediction. But something is missing from this picture. In layman's terms, counterfactual explanations inform an individual where they need to get to, but not how to get there, and this is called recommendation. We recall that a primary purpose of an explanation is to increase the individual's agency by offering ways to act in order to achieve recourse. Thus, the missing link in this diagram is this line here, corresponding to the set of actions the individual must perform to realize the desired situation. This is referred to as algorithmic recourse, and our work first shows that existing approaches fail in general settings to achieve recourse, and second, we suggest an alternative formulation to achieve optimal and feasible recourse in general. So let's look at the previous work. The problem setup is as follows. Edward, the individual seeking a loan, is represented by xf, FAcctual. The bank uses a classifier, h theta, shown in this example as a linear decision boundary, and Edward is denied a loan, and we seek to help him understand how to solve this situation, i.e. to achieve recourse. So the bank offers an explanation in the form of counterfactual explanations. The original counterfactual explanation problem was formulated by Valera et al. As this optimization problem here, to find the most similar individual or feature vector to the factual individual that is seeking recourse. This feature vector would obtain the desired outcome on the other side of the decision boundary. This is visually depicted using the two XCFEs, or hypothetical Edwards, in the figure. To shift the focus from explanations to recourse actions, Uston et al. Reformulated the optimization problem on the left as the one on the right, where now we optimize the cost of actions that would result in a counterfactual instance on the other side of the decision boundary. This is visually shown as the two deltas we see in the image. This reformulation allows adding feasibility constraints over the actions to account for the actionability of the features. For example, age cannot decrease, or an education degree can only be attained, or gender may be considered as immutable. This reformulation assumes that all features can be modified in an additive and independent manner, which may not be very realistic, as we'll see in a few slides. The question we ask in this work is, do these shifts or deltas given by previous approaches translate to optimal and feasible actions A for recourse? In this work, we argue that this question cannot be answered without considering the world in which the actions will be performed. The intuition is as follows. In general, features that go into the classifier do not need to be independent, and in fact, they generally are not. For example, features such as education level, salary, and savings are not invariant to the changes in one another. Changing one feature, such as education level, may have consequential effects, positive or negative, on other features such as salary or savings. These relations are captured in and modeled using a structural causal model M. Let's look at an example. Consider the following setting. Imagine Edward is a home seeker with a salary of $75,000 and a savings balance of $25,000. Consider a fixed predictor used by the bank, and imagine further the causal relations between these variables, where home seekers typically save 30% of their salary. The full SCM capturing this setup is shown on the right. In this setting, previous methods based on counterfactual explanations may return either of these two deltas, represented by the two green stars in the figure. A counterfactual explanation-based recourse action could then be carried out via a structural intervention on the set of variables in I, where the set I may be any arbitrary subset of the observed variables as long as the intervention contains the variable indices for which delta star I is not zero. This means that if delta star suggests a non-zero change to variable xi, the individual may perform an intervention on xi, setting its value to the factual value plus delta star I. This results in the point x star CFE, as we see on the bottom right in the figure. But we observe that there is a better solution, as shown by the blue star, or x star SCF, which stands for structural counterfactual, which only requires a 14% relative effort on the variable x1 in this example, as compared to a 33% effort on x1 or 20% effort on x2 in the CFE-based recourse actions. This is because A star is obtained by making use of the information about dependencies between variables as captured in the causal model M. In this example, there is a positive causal effect between variables, where an increased salary would also result, after some duration, in an increased bank balance. In this setting, previous methods suggested too much effort, leading to suboptimal recourse. However, it's easy to imagine the converse with negative causal relations between variables, where then previous approaches would suggest too little effort that don't even flip the prediction, leading to no recourse at all. We have an example of this in this paper, and we invite you to read it there. Therefore, beyond the suboptimality of using counterfactual explanations for recourse actions, it may be that the recommended actions do not even result in the desired outcome. Thus, to answer the question, do counterfactual explanations result in recourse, we say not in general. Now, this example provides the insight for the following key result in our work, which is that counterfactual-based actions, as we see on the top, in general guarantee recourse if and only if the set of descendants of the acted upon variables is the empty set. In practice, this translates to the fact that counterfactual explanations only guarantee recourse if and only if the features are independent of each other, which is an unrealistic assumption and does not hold in general settings, as we saw earlier. Alternatively, the individual may also intervene on the descendants of the intervened upon variables so that they can keep their factual value regardless of the counterfactual value of their parents. Unfortunately, this might be suboptimal, as we showed in the example of the previous slide, or directly infeasible, as it involves being able to intervene on all the variables. To solve this limitation, we propose to reformulate the recourse problem and instead of finding the minimum cost shift, we aim to find the minimum cost interventions. The key aspect of this reformulation, as highlighted here, is that we find such interventions via computing the structural counterfactual, which directly accounts for actions as well as the consequences of those actions towards the final outcome. We solve the new optimization problem by deriving closed-form expressions for the highlighted constraint using Pearl's three-step process for structural counterfactuals for the common family of additive noise models. We invite you to review the manuscript for more details on this derivation, as well as experimental demonstrations. Now, in the remaining slides, I would like to explore some more aspects of actions as interventions in the real world. Throughout this paper, we considered structural interventions, where each intervention proceeds by unconditionally severing all edges incident on the intervened upon node, fixing the post-manipulation distribution of a single variable to one deterministic value. While intuitively appealing and powerful, structural interventions are in many ways the simplest type of interventions, and as suggested by authors before us, their simplicity comes at a price, which is foregoing the possibility of modeling many situations realistically. Notably, there is nothing inherent to an SCM that a priori determines the form, feasibility, or scope of an intervention. I'd like to emphasize that the standard tools of the SCM framework do not inherently restrict interventions, and one could, at least in theory, intervene unconditionally on any subset of variables to perform counterfactual analysis. Thus, the choice of form, feasibility, and scope of interventions are delegated to the individual and/or to the institution, and are made based on a semantic understanding of the modeled variables. For an extensive discussion on these topics also, we invite you to review the manuscript. Here, we suffice to give one example. Once we start thinking about the world in a causal manner, and to think about actions as interventions, we are able to tease apart the definition of feasibility. While previous works only differentiated between mutable and immutable variables, also known as actionable versus non-actionable, for example, a bank balance is actionable but gender, for the purposes of obtaining a loan, is non-actionable, we can now describe a new form of variable, which is a mutable but non-actionable variable. An example of this is credit score, where intuitively the credit score is not directly actionable by the individual, but may change as a consequence of a change to its causal ancestors, for example, regular debt payment. Of course, this example assumes that a bank would not recommend fraudulent actions that may allow direct intervention on the variable credit score. Furthermore, we provide examples of hard versus soft interventions, otherwise known as structural versus additive interventions, as well as how to handle fat hand interventions, which are actions that may simultaneously require intervening on multiple variables. An example here is that finding a new job may simultaneously intervene on income and length of employment. In conclusion, we studied the problem of algorithmic recourse, focusing on consequential actions rather than explanations. We showed through examples and in theory that recourse is not guaranteed in general using counterfactual explanations. We argued to reformulate the optimization problem from finding nearest counterfactuals to finding minimum cost interventions that not only account for the actions themselves, but also the consequences of those actions, which together lead to more optimal and less costly recourse for the individual. Finally, we provide an extensive discussion on the various aspects of real-world actions as interventions. Of course, the primary limitation of our work is the assumption of knowledge of the true SCM governing the world. This is a major practical limitation as the SCM is typically not available. Thus, while in this work, we showed theoretically that recourse is not guaranteed in general using counterfactual explanations, in follow-up work we proved via contradiction that recourse can only be guaranteed if the true SCM is known. There, we also relaxed the assumptions made in this work and no longer require knowledge of the entire causal model, but only that of the causal graph, and propose two probabilistic approaches along with new optimization formulations with brute force and gradient-based solutions that would result in recourse with high probability, thus resolving the untestable assumptions about the SCM that would restrict their practical use. If you found the content of this presentation interesting, you can read the content of this manuscript as well as the follow-up work on arXiv. We hope to soon release a open source code for running all experiments here and in the follow-up work on GitHub. As always, please feel free to reach out via email if there are any questions or if you'd like to chat. Thank you very much.